72 hours from now, on December 19th, 2025, humanity will get its best look at something that's been traveling through space for millions of years, just to reach this moment. 3Io Atlas, the third interstellar object ever detected, is approaching Earth during the darkest night of the year with no moon to interfere, as if the cosmos itself arranged perfect viewing conditions. Scientists have pointed every available telescope at it, and what they're seeing doesn't quite fit. The polarization is extreme. The chemistry is alien. The jets wobble with eerie precision, and the sun, almost on cue, has erupted into chaos, filling our instruments with noise at exactly the wrong time. The countdown is on, and the next 72 hours matter more than any before it, because it could change everything we thought we knew about interstellar visitors. You'll want to stay close as 3i Atlas makes its approach. Subscribe now and follow along so you don't miss what happens when Atlas finally shows its true nature in 72 hours. The universe has secrets, and this channel has answers. The clock is running. Right now, as you hear these words, hundreds of telescopes across every continent are locked onto a single point in the night sky. Scientists are working in shifts, monitoring data streams that refresh every few minutes. Observation posts from Chile to Hawaii, from Australia to the Canary Islands, all pointed at the same target. They're racing against something that isn't a deadline in the traditional sense, but a cosmic appointment that was set millions of years ago when this object began its journey toward us. We have 72 hours until December 19th, 2025. That's when 3i Atlas reaches its closest approach to Earth, 1.8 astronomical units away, roughly 270 million kilometers. That sounds far, and it is. You're safe. Your family is safe. This isn't an extinction event. But distance isn't the issue here. The issue is what happens when we finally get our best look at something that has been defying explanation since the moment we discovered it. The timing couldn't be more perfect if someone had planned it. December 19th falls just after the new moon. Complete darkness. No lunar glare washing out the faint details that astronomers desperately need to see. It's the astronomical equivalent of turning off every light in the house so you can peer through the window at something moving in your yard. Something you're not quite sure about. Something that might be looking back. This is 3i Atlas, the third confirmed interstellar object ever detected. Think about that number for a moment. 3. In all of human history, with all our telescopes and detection systems, we've only confirmed 3 visitors from beyond our solar system. The first was Oumuamua in 2017, that strange tumbling cigar-shaped object that accelerated away from the sun in ways that simple outgassing couldn't fully explain. The second was Borisov in 2019, which behaved like a normal comet and almost bored us with its predictability. And now, we have Atlas, the third visitor, the one that's refusing to fit into either category. The name itself tells a story. 3i means third interstellar object. Atlas comes from the survey system that first spotted it, the Asteroid Terrestrial Impact Last Alert System in Hawaii. But unlike the previous 2 visitors, Atlas arrived with something extra. Something that has astronomers using words like unusual and unexpected and requires further study, which in scientific language translates roughly to, we don't know what we're looking at. Let's start with what we can see. The object glows green. Not metaphorically green, not greenish if you squint, but genuinely, vividly green when viewed through the right instruments. The Gemini Observatory captured images showing its coma, the cloud of gas and dust surrounding it, fluorescing in this characteristic color. The explanation is straightforward chemistry. Diatomic carbon molecules, C2 as chemists call it, absorb ultraviolet light from the sun and re-emit it in the green part of the spectrum. Comets do this. It's normal. Except the intensity and persistence of Atlas's green glow pushes at the edges of what we'd expect from a small icy body. Then, there's the anti-tail. Most people, if they know anything about comets, know that comet tails point away from the sun. Solar wind and radiation pressure push gas and dust outward, creating those iconic streaming tails that inspired terror and wonder in our ancestors. But Atlas shows something different, a persistent feature that appears to point toward the sun. Now, anti-tails aren't unknown. They're usually perspective effects, moments when Earth's position relative to the comet creates an optical illusion. Except Atlas's anti-tail doesn't behave like a simple perspective trick. The sunward jets persist. They show structure. They suggest something more complex is happening with how this object sheds material. The X-ray detection adds another layer. The XMM Newton Space Telescope picked up X-rays coming from Atlas. Again, not impossible. When solar wind, that stream of charged particles constantly flowing from the sun, collides with gases in a comet's coma, it can produce X-rays through a process called charge exchange. But the intensity matters. The structure matters. What XMM Newton saw tells us about how violently the solar wind is interacting with Atlas, about the composition of gases surrounding it, about activity levels that challenge our models of how small interstellar objects should behave. Hubble added its observations. The Space Telescope revealed jet structures that don't conform to simple sublimation patterns. When ice turns directly to gas on a comet's surface, it creates jets. Predictable, radial jets streaming away from hotspots on the nucleus. Atlas shows jets, but they're complicated. One appears to precess, wobbling like a spinning top, suggesting complex rotation. The coma itself has asymmetries that shouldn't be there if this were just a ball of ice and rock spinning through space. And there's the chemistry. The James Webb Space Telescope turned its infrared eye toward Atlas and found something peculiar in its composition. High levels of carbon dioxide relative to water. That ratio matters because it tells us about where an object formed, under what conditions, from what primordial cloud. Atlas's chemistry suggests a formation environment different from typical solar system comets, different from Borisov, consistent with an origin in a stellar system unlike our own. All of this is real data. Real observations from instruments that have proven themselves reliable across decades of operation. None of it requires conspiracy or speculation. But here's where we step from the comfortable realm of interesting science into territory that makes people uncomfortable. Because when you add up all these anomalies, all these unexpected features, you start to ask a question that sounds absurd until you realize it isn't. Was it always just a comet? Or did we classify it as a comet because that's what we expected to see? The human brain excels at pattern matching. We see what we anticipate seeing. When something comes from interstellar space and develops a tail and glows green, we call it a comet, because what else would we call it? But what if the object itself is trying to tell us something different through every wavelength of light we measure, through every spectral line we analyze, through behavior that consistently defies simple explanation? The sun isn't helping. Recent weeks have seen monster sunspot groups form and rotate across the sun's face. X-class flares, the most powerful classification, have erupted multiple times. This is normal for a star in its active phase, nothing apocalyptic, but the timing creates complications. Solar storms distort data. They saturate detectors. They create noise in radio observations and can even affect space-based telescopes. When you're trying to extract subtle signals from an object millions of kilometers away, having the sun throw electromagnetic tantrums is like trying to hear a whisper during a rock concert. Some might call it coincidence. The sun operates on an 11-year cycle, and we're in an active period. It has nothing to do with Atlas, except coincidences pile up in ways that make scientists nervous. not because they believe in cosmic conspiracies, but because they know how easily real signals can be lost in noise, how a critical observation window can be ruined by factors beyond anyone's control. So we have 72 hours. 72 hours of optimal darkness before the moon returns and drowns out the faint details. 72 hours while the world's best instruments point upward and capture every photon they can. 72 hours to answer a question we're almost afraid to ask directly. And after December 19th, Atlas will begin its long fade, moving away from the sun, dimming, becoming harder to study. If there's something to discover, something hidden in those jets and that green glow and that impossible chemistry, we need to find it now, before it's gone, before we're left with fragments of data and a growing suspicion that we missed something crucial. The stage is set. The object is approaching. The telescopes are ready. What happens next depends entirely on what Atlas chooses to reveal in the darkness. Scientists don't use the word weird in their papers. They prefer anomalous, or requiring further investigation, or, my personal favorite, not fully consistent with current models. These are the polite ways astronomers tell each other that something is breaking the rules. Atlas is breaking a lot of rules. Let's talk about light. Not the light you see with your eyes, but the full spectrum of electromagnetic radiation that tells us what objects in space are made of, how they're moving, how they're behaving. Every atom, every molecule has a signature. When you heat them up or shine light on them, they absorb and emit specific wavelengths. It's like a fingerprint, unique and identifiable. When we point our instruments at Atlas, we're not just taking pretty pictures. We're reading its fingerprints, and some of those fingerprints don't match anything in our database. The polarization data is where things get genuinely strange. Light is a wave, and like all waves, it can vibrate in different directions. Polarization measures those directions. When sunlight bounces off particles in a comet's coma, the way it polarizes tells us about the size, shape, and composition of those particles. Researchers analyzing Atlas found polarimetric signatures that are extreme. The particles in its coma are scattering light in ways that differ substantially from typical comets. This suggests the dust grains have unusual properties. Maybe they're unusually large. Maybe they're made of materials we don't normally see. Maybe they're shaped differently than the irregular chunks we expect from natural ice sublimation. This matters more than it might seem. The dust in a comet's coma is the debris of its nucleus, the solid core at the center. If that dust is weird, the nucleus is weird. If the nucleus is weird, we need to rethink what this object actually is. Then we come back to that chemistry. James Webb didn't just detect carbon dioxide. It detected it in abundance. The ratio of carbon dioxide to water is significantly higher than what we see in solar system comets. Now, comets vary. Some are water-rich, others have more CO2, and this depends on where and how they formed. But Atlas's ratio is pushing boundaries. It suggests formation in a cold, carbon-rich environment, perhaps around a star very different from our sun, perhaps in a molecular cloud with chemistry unlike the one that birthed our solar system 4.6 billion years ago. But here's where it gets interesting. High CO2 means the object is extremely active, even at distances where water ice doesn't sublimate efficiently. Carbon dioxide turns to gas at lower temperatures than water. So Atlas was probably outgassing, probably developing its coma and tails, long before it got close to the sun. That means somewhere out beyond Neptune's orbit. While most comets are still frozen solid, Atlas was already awake, already active, already doing something. The jet behavior compounds the mystery. That precessing jet Hubble observed isn't just wobbling randomly. It's periodic. It suggests the nucleus is rotating, And that rotation isn't simple. Maybe the nucleus has an irregular shape. Maybe it's tumbling on multiple axes. Or maybe, and this is where we enter speculative territory, something about its internal structure is causing asymmetric outgassing that torques the object in complex ways. Imagine a balloon you inflate and then release without tying it off. It flies around the room in chaotic patterns because air escapes unevenly. A comet nucleus with active vents positioned asymmetrically could do something similar, creating complex rotational dynamics. Except balloons are manufactured objects with predictable geometry. Natural comet nuclei, formed from the random accretion of ice and dust, shouldn't have the kind of organized structure that produces such regular periodic behavior, unless they're not entirely natural. Wait, let's pause there. That sentence just triggered every skeptical instinct you have, and rightfully so. The jump from unusual jet patterns to artificial structure is enormous. It's the kind of leap that gets scientists laughed out of conferences. But we're going to explore it anyway, not because it's likely, but because the data keeps pushing us toward uncomfortable questions. Ground-based radio telescopes have been monitoring Atlas continuously. They're listening for anything that might suggest technological activity, modulated signals, regular pulses, anything that breaks from the random noise of natural electromagnetic emissions. So far, nothing. The radio spectrum is clean. Whatever Atlas is, it's not broadcasting. Or if it is, we're not recognizing the transmission for what it is. That absence of radio signals is important. It's evidence. Not conclusive evidence that Atlas is entirely natural, but strong evidence that it's not behaving like any hypothetical probe or spacecraft we might imagine. If an advanced civilization sent something on an interstellar journey, wouldn't it communicate? Wouldn't it emit signals we could detect? The silence suggests either there's nothing artificial about Atlas, or any technology involved is so different from ours that we literally can't recognize its emissions as signals. Let's compare this to our previous interstellar visitors. Oumuamua was the troublemaker. It accelerated away from the sun faster than gravity alone could explain. The leading explanation is outgassing, but Oumuamua showed no visible coma, no tail, no evidence of the volatile materials that should create that acceleration. Some scientists proposed exotic explanations: light sails, hydrogen icebergs, solid nitrogen debris from a Pluto-like world. Each theory had problems. None fit perfectly. Oumuamua left our solar system with its mysteries intact. Borisov was the good student. It behaved exactly as a comet should. Normal composition, normal tail, normal orbit. It came from interstellar space, but acted like a solar system comet that just happened to be passing through. Boring in the best possible way, because it confirmed our models work. Atlas sits between these extremes. It has a coma. It has tails. It's clearly outgassing. But the details are wrong. The composition is off. The jets are too organized. The polarization is too extreme. The chemistry is too unusual. It's like a student who gets 90% of the test correct, but fails spectacularly on the remaining 10%, in ways that suggest they're answering a different test entirely. The scientists studying Atlas are professional skeptics. They've built careers on questioning assumptions and demanding evidence. They're not jumping to conclusions. But in private conversations, in the careful language of academic papers, you can sense unease, a recognition that this object doesn't fit comfortably into our categories, that maybe our categories aren't as complete as we thought. So what do we do with an object that acts like a comet but shows features that challenge comet physics? We could expand our models, add new parameters, invent new processes that might explain the observations while keeping everything safely natural. Scientists are good at this. They're flexible. They adapt theories to fit data. Or we could sit with the discomfort a little longer. Acknowledge that 3 interstellar objects is a tiny sample size. That our understanding of what's possible in other star systems in other formation environments, in the galaxy at large, might be far more limited than we'd like to admit. That the universe is under no obligation to make sense to us on our terms. The observations continue. Every night, when Atlas rises above the horizon, telescopes track it. Spectroscopes break its light into components. Cameras capture its changing appearance. Radio dishes listen for whispers. The data accumulates, and with it, the questions multiply. Because the more we see, the less certain we become about what we're actually looking at. There's a character in this story we haven't properly introduced yet. A character that's been ominously quiet until recently, and whose sudden awakening complicates everything. That character is the Sun. Our star is currently in solar cycle 25, approaching what's called solar maximum. This is the peak of its 11-year activity cycle, when sunspots proliferate and solar flares become frequent. The Sun's magnetic field, which generates all this activity, is a tangled mess right now. Field lines twist and reconnect in explosive events that release energy equivalent to billions of nuclear weapons. This is normal. The Sun has been doing this for billions of years. But normal doesn't mean irrelevant. In recent weeks, we've seen sunspot groups that stretch across hundreds of thousands of kilometers of the Sun's surface. These dark regions, cool spots in the photosphere where strong magnetic fields suppress convection, are factories for solar flares. And the Sun has been productive. X-class flares, the most powerful category we classify, have erupted multiple times. Each one releases a burst of radiation across the electromagnetic spectrum, from radio waves to X-rays to gamma rays. Each one sends a shockwave through the solar wind, that constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. These eruptions affect us here on Earth. They create geomagnetic storms that light up auroras and occasionally disrupt power grids and satellite communications. They're beautiful and dangerous in equal measure. But for astronomers trying to study Atlas, they're a nightmare. X-rays from solar flares saturate detectors. Imagine trying to photograph a firefly while someone keeps flashing a spotlight in your direction. Space-based telescopes operating in high-energy wavelengths have to contend with this constant bombardment. They can filter some of it out, compensate for known patterns, but there's noise in every observation. Signal-to-noise ratio is everything in astronomy. When the noise goes up, subtle features disappear. Details get lost. And Atlas is all about subtle features that don't make sense. Radio observations face similar challenges. The Sun is a powerful radio source under normal conditions. During a flare, it becomes overwhelming. Radio telescopes trying to detect faint emissions from Atlas have to navigate around this interference. They observe when the Sun is below the horizon, or they use clever techniques to subtract its contribution from their data. But you can't subtract what you can't perfectly model, and solar flares are chaotic. Everyone is different. Everyone adds uncertainty. Then there's the solar wind itself. That flow of charged particles creates a bubble around our solar system called the heliosphere. Everything inside that bubble is bathed in solar wind. When that wind hits a comet's coma, hits the gases and dust surrounding the nucleus, it creates interactions. The X-rays XMM Newton detected from Atlas come from this interaction. Solar wind ions steal electrons from neutral atoms in the coma, and the energy released emerges as X-rays. This is known physics, except the intensity and structure of those X-rays depend on both the solar wind's properties and the coma's composition. When the solar wind is turbulent, when it's been disturbed by flares and coronal mass ejections, parsing out, what's happening becomes exponentially harder. Some have noticed the timing. Atlas reaches its closest approach during a period of heightened solar activity. Is this meaningful? Almost certainly not. The Sun doesn't respond to passing comets. There's no physical mechanism for a small object millions of kilometers away to influence stellar behavior. The idea is absurd. Except our brains are wired to find patterns, and when two unusual events coincide temporally, we can't help but wonder. This is where skepticism becomes crucial. Yes, the timing is interesting. Yes, it creates observational challenges. No, it doesn't imply causation. The sun is active because of its internal magnetic dynamo, processes driven by convection and differential rotation that have nothing to do with Atlas. Any appearance of connection is coincidence, but coincidences in science can blind us. They can cause us to miss the real signal while we're distracted by an imaginary pattern. The practical impact is straightforward. Solar activity increases the difficulty of observations right when those observations matter most. It's like someone turned up the difficulty setting on an already challenging game. Scientists are adapting. They're using multiple instruments to cross-check their findings. They're waiting for gaps in solar activity to grab their best data. They're applying more sophisticated analysis techniques to separate solar noise from genuine Atlas signals. But there's something else worth considering. Something that doesn't get discussed openly because it sounds too much like speculation. If you were an interstellar object, not necessarily intelligent, but perhaps equipped with some form of passive response system, when would you want to reveal your true nature? When would you feel safe showing capabilities beyond what observers expect? Maybe during a period when those observers are distracted, when their instruments are compromised, when attributing unusual behavior to solar interference would be easy and convenient. This is pure speculation, understand. There's no evidence Atlas is doing anything intentionally. But if we're exploring possibilities, if we're asking what-if questions, then the timing of solar maximum becomes less about coincidence and more about opportunity. Coronal mass ejections add another variable. These are massive eruptions of plasma and magnetic field that the sun occasionally hurls into space. When one heads toward Earth, it takes a day or two to arrive, and then it slams into our magnetosphere with dramatic results. Satellite operations get dicey. GPS accuracy degrades. Radio communications can black out at high latitudes. And any space-based observatory caught in the onslaught has to weather a storm of charged particles that can damage sensitive electronics and corrupt data. Atlas is out there beyond Earth's orbit, beyond our protective magnetic field. It's exposed to the full force of the solar wind and whatever storms come with it. There were ever a time when the object's true behavior might be masked by environmental chaos. This is it. Scientists are aware of this. They're factoring it into their analyses. But factor in only works if you know all the variables, and space weather is notoriously unpredictable. The sun, in its own way, is running interference. Not maliciously, not purposefully, but effectively, nonetheless. It's creating a fog through which we're trying to discern the truth about Atlas. And in 72 hours, when Atlas makes its closest approach, that fog will still be there. The sun will still be active. The instruments will still be fighting noise. Whatever we learn about Atlas will come through this filter of solar chaos, which leaves us with an uncomfortable question. If Atlas reveals something extraordinary on December 19th, something that challenges everything we think we know, will we even recognize it through the interference? Or will we attribute it to solar effects, to data artifacts, to anything except the possibility that we're seeing something genuinely unprecedented? The sun doesn't care about our questions. It burns and flares and erupts according to its own physics. But its indifference might be the biggest obstacle we face in understanding what's approaching us in the darkness. There's a technique in detective work called process of elimination. You list everything the suspect could be, then systematically rule out options until you're left with the truth. Astronomers do something similar when they encounter an unknown object. They start with the simplest explanation and work outward only when the evidence demands it. So let's follow that process with Atlas. Let's start with Comet, and see how far we get before the explanation breaks. Comets are dirty snowballs. That's the textbook description, though it's a bit reductive. They're mixtures of water ice, frozen gases, rocky material, and complex organic molecules, all jumbled together in a nucleus that's usually a few kilometers across. When a comet approaches the sun, solar heating causes the ices to sublimate, turning directly from solid to gas. This creates the coma and tails that make comets visually spectacular. It's straightforward physics. We understand it well. Atlas has a coma. Check. Atlas has tails. Check. Atlas brightened as it approached the sun. Check. By these basic criteria, calling it a comet seems perfectly reasonable. Except comets, like people, have tails. Little behavioral quirks and compositional signatures that help us understand their history and nature. And Atlas's tails are strange. Start with that polarization data again, because it really is remarkable. When researchers measured how light scatters off particles in Atlas's coma, they found values that sit at the extreme end of what's been recorded for any comet. Polarization depends on particle properties: size, shape, composition, internal structure. For Atlas to produce such extreme polarization, it's dust. Particles have to be fundamentally different from typical comet dust. Maybe they're larger, but larger particles require more energy to lift off the nucleus surface. You need vigorous outgassing to launch them, and while Atlas is clearly active, its size and distance from the sun don't suggest the kind of extreme activity that would loft unusually large particles efficiently. Maybe they're weirdly shaped, except dust particles from sublimating ice tend toward irregular but statistically predictable shapes. The random fracturing and sublimation of ice creates a certain range of geometries. Atlas's particles seem to be outside that range. Maybe they're compositionally unusual. This is where things get interesting, because the spectroscopy supports this. That high carbon dioxide to water ratio isn't just a chemical curiosity. It implies the nucleus formed under conditions where CO2 was more abundant than water, or where water was depleted relative to carbon dioxide. Either scenario points to a formation environment very different from the solar nebula that created our solar system's comets. Interstellar space is diverse. Stars form from molecular clouds with varying compositions. Some clouds are carbon-rich. Others have different elemental ratios based on the prior generations of stars that enrich them with heavy elements. Atlas might have formed around a star that went through different evolutionary stages than our Sun, in a cloud seeded with different supernovae debris. That would explain its unusual chemistry while keeping everything natural. But then we have those jets. That precessing, wobbling jet structure that Hubble observed. Comets can have multiple jets. They can have jets that turn on and off as the nucleus rotates and different areas face the sun. But organized, periodic precession suggests either a very specifically shaped nucleus with very specifically positioned active vents, or something about the object's internal structure that's driving asymmetric outgassing in regular patterns. The word regular should bother you. Nature loves chaos, randomness, asymmetry. When you see regular patterns, periodic behavior, organized structure, it often means something is constraining the system. Gravity creates regular orbits. Magnetic fields create regular shapes in plasmas. Crystalline structure creates regular atomic arrangements. What would create regular jet precession in a comet nucleus? One possibility is that the nucleus has a large internal cavity, a void space where volatile ices can sublimate internally before escaping through specific vents. As gas builds up pressure inside the cavity and then vents, it could create thrust that torques the nucleus in predictable ways. This isn't unprecedented. Some scientists think Oumuamua might have been a mostly hollow shard, which would explain its strange acceleration without visible outgassing. But cavities in comet nuclei are supposed to be rare. They require specific formation, Conditions or internal processes that excavate material. They're not the default structure. If Atlas has a significant internal cavity, we need to explain why. Was it always hollow? Did something hollow it out? Did it form that way through some unusual process? The alternative, the one that makes scientists uncomfortable, is that the regular behavior reflects artificial structure, designed geometry, purposefully placed vents or mechanisms that create the observed patterns. This sounds like science fiction, and maybe it is, but the data doesn't care about our comfort level. The data shows what it shows. Let's be clear about something. No one has detected artificial signals from Atlas. No radio transmissions. No modulated light. No evidence of technology. The assumption of natural origin is still the most reasonable starting point. But most reasonable and definitely correct aren't the same thing. When an object shows multiple unusual features that strain natural explanations, when it sits at the boundary of what our models can accommodate, intellectual honesty requires we at least examine alternatives. Oumuamua forced this conversation already. Its acceleration, its tumbling rotation, its bizarre elongated shape all sparked debate about whether it could be artificial. The consensus landed on natural explanations, but fragile ones. Explanations that required special circumstances and unusual conditions. Atlas is doing something similar. It's forcing us to stretch our models, to invoke rare scenarios, to explain away each anomaly individually, rather than seeing them as part of a coherent whole. What would an artificial interstellar object look like? We don't know. We've never built one. Our only interstellar probes, Voyagers 1 and 2, are tiny and slow and have only just begun leaving the solar system after decades of travel. An advanced civilization capable of interstellar travel might build probes we couldn't recognize. They might use materials and propulsion systems and operational strategies so different from ours that we'd misidentify them as natural objects. This is the dark forest problem in observational astronomy. If you don't know what you're looking for, if the thing you're looking for is deliberately avoiding obvious detection, how do you find it? You're left studying anomalies, looking for things that don't quite fit, following the trail of subtle wrongness that might lead to something genuinely unexpected. Atlas's chemistry is wrong for a solar system comet. Its polarization is wrong for typical dust. Its jet behavior is wrong for random sublimation. Its timing, arriving during solar maximum, creates observational challenges. Each wrongness has a possible natural explanation. But how many possible explanations do we stack up before we admit the simple explanation might not be correct? The scientific method demands skepticism. Extraordinary claims require extraordinary evidence. An artificial interstellar probe is an extraordinary claim. The evidence so far doesn't meet that standard. Atlas could be an unusually active interstellar comet with composition reflecting its alien origin, and that would be remarkable enough. Discovering that comets from other star systems can be substantially different from ours would revolutionize our understanding of planetary system formation and evolution. But part of us, the part that looks at the night sky and wonders what else is out there, can't help but question whether we're seeing the full picture. Whether the object now approaching, glowing green in the darkness, carrying its strange chemistry and organized jets and extreme polarization, is really just a comet, or whether it's something we don't have a name for yet. December 19th will bring answers. Maybe not the answers we expect. Maybe not answers at all. Just more questions. But the observations will continue. The data will accumulate. And eventually, we'll know more about what Atlas truly is. Whether we'll understand it is another matter entirely. The internet is not a place where nuance thrives. It's where information goes to be simplified, amplified, and mutated into forms its creators wouldn't recognize. Atlas landed in this environment the moment it was discovered, and the narratives that grew around it tell us as much about human psychology as they do about interstellar objects. You can find them if you know where to look. Forums dedicated to space anomalies. Subreddits analyzing every data release. YouTube channels with titles in all caps promising breaking revelations. They've latched onto Atlas with enthusiasm, and their theories range from plausible to fantastical to genuinely creative in their disregard for physics. The most common theme is non-gravitational acceleration. This mirrors the Oumuamua debate, where the object's trajectory couldn't be explained by gravity and solar radiation pressure alone. People took that anomaly and ran with it. Some proposed Oumuamua was an alien light sail, a thin reflective structure pushed by starlight. Others suggested it was debris from a Dyson sphere or a derelict spacecraft tumbling through the galaxy. These ideas gained traction, not because evidence supported them, but because they filled a narrative void. They gave people a story more interesting than weird comet we don't fully understand. Atlas is getting similar treatment. Claims circulate that it's performing maneuvers, changing course, showing signs of intelligent control. These claims typically misunderstand orbital mechanics. Any object influenced by multiple gravitational sources, the sun, planets, the galactic tide, follows a complex path. Small perturbations are normal. Apparent course changes are often just artifacts of observation geometry or the accumulation of tiny forces over time. But explaining this requires math and patience, while claiming it changed direction requires only a screenshot and speculation. Some theories invoke energy deficits. They claim Atlas is too bright for its size and distance, that it's emitting more energy than solar heating can explain. This is actually worth examining, not because it's likely correct, but because it touches on real observational challenges. Brightness in comets depends on numerous factors. Albedo, the reflectivity of the surface. Activity level, how much gas and dust are being produced. Grain size distribution in the coma. Viewing geometry. All of these can vary, and all of them make predicting brightness complicated. If Atlas appears brighter than naive models predict, it might mean those models are incomplete. It might mean the object has a higher albedo than typical comets. It might mean its activity level is unusually high. Or yes, in principle, it could mean there's an additional energy source. But jumping from brighter than expected to artificial power source skips about a dozen more mundane possibilities that should be eliminated first. The psychology behind these narratives is understandable. We live in an era of unprecedented access to information. Anyone can download astronomical data, analyze images, run calculations. This democratization is wonderful. It engages public interest and sometimes yields genuine discoveries. But it also means people without training in how to interpret data, without understanding systematic errors and calibration issues, and the 1,000 ways observations can mislead, are drawing confident conclusions from incomplete information. There's also a deeper hunger at work, a desire for the universe to be more than it appears, for life, intelligence, purpose to be common rather than rare, for humanity to be part of a larger cosmic community rather than alone on a tiny world in an indifferent galaxy. Atlas, strange and unexplained, becomes a vessel for these hopes. If it's artificial, if it's a probe from another civilization, then we're not alone. Everything changes. The universe becomes a different place. Scientists feel this too. They're human. They want to discover something extraordinary. But they're trained to separate what they want from what the evidence shows. They're comfortable with uncertainty, with saying, "We don't know yet," and meaning it. The public often isn't. We want answers. We want them now. And if the experts won't provide them, we'll create our own. The data gaps contribute to this. Astronomical observations are inherently limited. We can only observe objects during certain windows. We can only measure certain properties with available instruments. We're always working with incomplete information. building models that fit what we can see while acknowledging vast areas of uncertainty. Professional astronomers understand these limitations. They factor them into their conclusions. But from the outside, those gaps look suspicious. They look like hiding places for secrets. When official sources say, "We need more data," or "This requires further study," some people hear, "We're not telling you everything." Mistrust of institutions, earned or not, colors how information is received. Add the internet's tendency to amplify contrarian voices, and you get an environment where speculation spreads faster than careful analysis. The role of media outlets complicates this further. Some report astronomy news responsibly, conveying both the excitement of discovery and the uncertainty of interpretation. Others prioritize clicks. They take preliminary findings and present them as definitive. They use sensational headlines that promise more than the actual research delivers. This creates confusion, and when the sensational claims don't pan out, breeds cynicism. Atlas suffers from all of these factors. It's genuinely unusual, which gives speculation a foothold in reality. It's distant and hard to study in detail, which creates information gaps. It's arriving during a time of heightened solar activity, which adds observational complexity that can be misinterpreted as evasion or interference. And it's the third interstellar object, making it part of an emerging pattern that our brains desperately want to understand, even if the sample size is too small for real conclusions. So what's the responsible way to handle this? How do we engage with Atlas's mysteries without falling into conspiracy or dismissing legitimate questions? The answer starts with epistemic humility, admitting what we don't know, distinguishing between "this is weird" and "this is evidence of X," being willing to explore unlikely possibilities while proportioning our confidence to the strength of evidence. The scientific process isn't quick. It's iterative, collaborative, and self-correcting. Papers get published. Other scientists review them. Debates happen. More data arrives. Theories get refined or discarded. This takes time. Months. Years, sometimes. The internet operates on a different timescale. It wants answers in hours. This mismatch creates friction. Atlas will teach us something. Maybe it teaches us about the diversity of interstellar objects and the varied environments where comets can form. Maybe it teaches us about solar-wind interactions with unusual compositions. Maybe it teaches us that our models need substantial revision. Or maybe, just maybe, it teaches us that the universe is stranger than we imagined, and that recognizing artificial structures in space is harder than we assumed. But whatever Atlas teaches us, the lesson will come from data, not speculation. From careful observation and rigorous analysis, not from viral posts and breathless videos. The truth about Atlas exists independent of our theories about it. The object is what it is. Our job is to figure out what that is, and to do it honestly. Let's play a game, a thought experiment. Let's assume, just for the next few minutes, that Atlas isn't a comet. Let's assume the anomalies aren't quirks of unusual chemistry or rare but natural processes. Let's assume we're looking at something that requires explanation outside conventional astrophysics. What would that mean? What would it look like? And critically, how would we know? The first thing to understand is that artificial doesn't mean obvious. Our assumptions about what technology looks like are based on human technology. Metal, electronics, energy consumption, communication. But we've been building things for maybe 10,000 years if we're generous. An alien civilization could have millions or billions of years of development behind them. Their technology might be so advanced, so different from ours, that we literally lack the conceptual framework to recognize it. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. We can extend that. Any sufficiently advanced technology might be indistinguishable from nature. It might mimic natural processes so perfectly that our instruments read it as a comet or asteroid. It might use materials and energy sources that don't register on our sensors as artificial. It might operate on principles we haven't discovered yet. So if Atlas were artificial, if it were some kind of probe or vessel, how would it behave? Probably not like a spacecraft in a movie. No bright lights, no radio signals, no obvious propulsion. Instead, it might use the environment. Solar radiation for power. Gravity for trajectory adjustments. Natural outgassing as camouflage. It might look almost exactly like a comet, with only subtle deviations that require careful analysis to detect. Those jets we discussed, the ones with organized precession, could be natural. Or they could be thrust vectoring. Controlled release of material to fine-tune the trajectory. If you wanted to visit the inner solar system, but didn't want to look like an obvious artificial object, mimicking a comet would be brilliant strategy. Comets are expected. They're understood, or we think they are. A comet doesn't trigger alarm. It triggers scientific interest, but not panic. The chemistry could be deliberate too. That high carbon dioxide ratio might not reflect where Atlas formed, but what it's choosing to vent. CO2 is easier to produce than water through chemical processes. If you're an artificial object trying to maintain a comet disguise, using CO2 for course corrections while minimizing water emission might be more efficient. This all sounds insane. It probably is. But let's follow it further, because the thought experiment reveals something important about how we approach unknown phenomena. If Atlas were artificial and trying to remain undetected, it would likely succeed. Our detection methods assume natural objects. We look for gravitational effects, spectral signatures, brightness variations, all interpreted through models of comets and asteroids. An object designed to match those models would slide right through our classification system. The only way we detect artificiality is through anomalies, things that don't quite fit, which is exactly what we're seeing with Atlas. The extreme polarization, the unusual jets, the chemistry that pushes boundaries, each individually explainable, but together forming a pattern of wrongness that keeps catching attention. Now, let's consider purpose. If Atlas were artificial, why would it be here? The most common speculation is reconnaissance, survey missions, studying solar systems to catalog them, looking for interesting planets, maybe searching for signs of technological civilization. Earth broadcasts radio waves into space. We've been doing it for a century. Any nearby star systems could detect us. If someone decided to investigate, an interstellar probe might be their first step. The trajectory matters here. Atlas isn't heading straight for Earth. Its closest approach is 1.8 astronomical units, way outside Earth's orbit. If reconnaissance is the goal, that's a reasonable observation distance. Close enough for detailed study, far enough to avoid immediate detection or confrontation. You'd park just outside the target's sphere of influence and observe. The timing matters too. Arriving near solar maximum means Earth's attention is divided. Space weather monitoring competes with Atlas observations. Data is noisier. Attributing unusual behavior to solar effects is easy. It's the perfect cover. Again, this is speculation built on speculation, but the thought experiment has internal logic. What about communication? If Atlas were artificial, wouldn't it try to contact us? Maybe, or maybe not. Consider how we design an interstellar probe. We'd probably make it autonomous, capable of making decisions without real-time input from home, because light speed delays make remote control impossible across interstellar distances. We'd give it protocols, rules for behavior, and one rule might be, observe only, do not engage unless certain conditions are met. Those conditions might not include primitive civilizations like ours. We're barely spacefaring. We've sent probes to other planets, but haven't established permanent presence beyond Earth. From an advanced civilization's perspective, we might not be worth contacting yet. We might be cataloged and left alone until we mature. Or the probe might not be from an active civilization at all. It could be ancient, a relic from a civilization long gone, still following its programming billions of years after its creators vanished. The galaxy is old. Civilizations could rise and fall on timescales we can barely comprehend. Their artifacts might outlast them, wandering between stars, executing missions that no longer have purpose. This is getting dark, but the darkness is part of the thought experiment. If we're wrong about Atlas being natural, if it's artificial, that doesn't necessarily mean first contact. It might mean we're seeing echoes of civilizations past, ghosts in the machine, technology outliving its makers. Let's come back to physics, because that's where speculation meets reality. If Atlas has an internal power source, something beyond what solar heating and stored volatiles can provide, it should be detectable. Excess heat emission, anomalous radiation, something that violates conservation of energy. We haven't seen that. Thermal observations show temperatures consistent with solar heating, no excess energy, no unknown power sources. But that assumes we'd recognize the signature. That assumes alien technology uses energy in ways we'd detect with our instruments. Maybe it's incredibly efficient. Maybe it operates on principles where waste heat is minimal. Maybe it uses quantum effects or space-time manipulation or something we don't have physics words for yet. Absence of expected signatures doesn't prove absence of technology. It just means if technology is there, it's beyond our current ability to characterize. The probability of all this is vanishingly small. The universe is under no obligation to be dramatic. Most of the time, when something looks like a comet, it's a comet. Occam's razor, the principle that simpler explanations are more likely, strongly favors natural origin. Every scientist working on Atlas knows this. They're exploring natural explanations first because those are far more probable. But probability isn't certainty. Low likelihood isn't zero likelihood. And when we're dealing with interstellar objects, with visitors from beyond our solar system, we're in genuinely unexplored territory. We have a sample size of 3. Oumuamua, weird. Borisov, normal. Atlas, weird again. That's not enough data to say what typical even means for interstellar objects. So we observe, we measure, we analyze, we build models and test them against data. And if the data keeps refusing to fit, if the anomalies persist and multiply, eventually we might have to consider possibilities that currently seem absurd. Not because we want them to be true, but because the evidence demands it. December 19th approaches. The closest approach, the moment of maximum observational opportunity. Whatever Atlas is, we'll get our best look at it then. And maybe, just maybe, it will show us something that forces us to rethink everything we thought we knew about what's possible in the cosmos. Atlas exists within a context. It's not an isolated mystery, but part of larger stories playing out across space and time. To understand its significance, we need to zoom out, way out, to the scale of solar systems and galaxies and the ongoing human project of understanding our place in all of it. Let's start with the Sun, because it's been a character throughout this narrative. Our star is currently active, throwing flares and coronal mass ejections with impressive frequency. This is phase of solar maximum, the peak of cycle 25. Understanding solar cycles matters for more than just Atlas observations. It matters for Earth's technology infrastructure, for satellite operations, for power grids that can be disrupted by geomagnetic storms. Space weather is real. Weather, and it affects us. The giant sunspot groups we're seeing now are magnetic anomalies where the sun's internal field breaks through the surface. These regions are cooler than surrounding photosphere, which is why they look dark, but they're still hot enough to vaporize any known material. They're also sites of intense magnetic energy storage. When that energy releases, when field lines snap and reconnect, we get flares. X-class flares release roughly 10 million times the energy of a volcanic eruption in seconds. That's the scale we're dealing with. These flares don't just affect our observations of Atlas. They affect everything we do in space. The International Space Station has to monitor solar activity constantly. Astronauts can be endangered by radiation from major events. Satellites in high orbits, above Earth's protective magnetosphere, can suffer damage. GPS systems lose accuracy during geomagnetic storms. We've built a technological civilization that extends into space, and that extension makes us vulnerable to solar tantrums. Beyond solar physics, Atlas fits into the emerging field of interstellar object studies. We've only been capable of detecting these visitors for a few years. Our survey telescopes, the systems that automatically scan the sky looking for moving objects, are relatively new. Before them, interstellar objects could have passed through our solar system unnoticed. We simply weren't looking carefully enough. Now we are. Surveys like Pan-STARRS and Atlas, the system that found this comet, scan large portions of the sky repeatedly. They detect asteroids that might threaten Earth, but they also catch interstellar objects moving too fast to be bound to the sun. The more we look, the more we'll find. Current estimates suggest 1 or 2 interstellar objects of detectable size pass through the inner solar system each year. Most we miss. Some we catch. This changes our understanding of the galaxy. Interstellar space isn't empty. It's populated with debris, with rogue planets ejected from their birth systems, with comets scattered by gravitational interactions, maybe with other things we haven't imagined. These objects carry information about their origins. Studying them is like receiving messages from distant stellar systems, postcards from places we can't yet visit. The diversity we're seeing among interstellar objects is itself significant. Oumuamua's strange acceleration and lack of visible coma, Borisov's perfectly normal comet behavior, Atlas's unusual chemistry and jet patterns. Each is different. This suggests planetary systems around other stars form objects under wildly varying conditions. Some systems might produce comets like ours. Others might create something entirely different. The galaxy is a laboratory, and every interstellar visitor is a sample from a different experiment. Planetary defense networks are using Atlas as a test case, not because it threatens Earth, but because tracking and characterizing fast-moving interstellar object provides valuable practice. If something dangerous ever does approach, we need protocols. We need international cooperation. We need the ability to quickly determine an object's trajectory, composition, and risk level. Atlas is a drill, a real-world exercise in global coordination and rapid response. Multiple space agencies and research institutions are collaborating on Atlas observations. Data is being shared in near real time. Observatories in different hemispheres coordinate to provide continuous coverage. This is modern astronomy at its best. A global effort focused on a single target, bringing together expertise and resources from around the world. The results will inform how we handle future visitors, whether they're scientifically interesting or potentially dangerous. Looking ahead, Atlas has another appointment. In March 2026, it will pass relatively close to Jupiter. Not close enough for a collision, but close enough for significant gravitational interaction. Jupiter is massive, 300 times Earth's mass. When small objects pass near it, their trajectories bend sharply. For Atlas, this encounter will change its path through the solar system. It might get ejected entirely, flung back into interstellar space. Or it might be captured, doomed to orbit the sun for millennia. That Jupiter encounter will give us additional data. We'll see how Atlas responds to changing gravitational environment. We'll observe whether its activity level changes as it moves further from the sun. If there are any remaining mysteries about its composition or structure, the Jupiter Pass might provide clarifying information. It's a second chance, a bonus round in our attempt to understand this object. Beyond Atlas specifically, the future of interstellar object research looks promising. New telescopes coming online will detect fainter, more distant objects. The Vera C. Rubin Observatory, currently under construction in Chile, will revolutionize transient astronomy. Its large mirror and advanced camera will scan the entire visible sky every few nights, catching anything that moves or changes. It will find dozens, maybe hundreds, of interstellar objects over its operational lifetime. Each discovery will add to our understanding. We'll build a catalog of interstellar compositions. We'll learn what planetary systems typically eject and why. We'll develop better models of star formation and system evolution. And maybe, just maybe, we'll find something that doesn't fit any model. Something that forces us to expand our conception of what's possible. There's also discussion of missions. Sending spacecraft to intercept interstellar objects. This is technically challenging because these objects are moving fast and their trajectories are unpredictable. But it's feasible. A probe launched with enough advance warning could rendezvous with an interstellar visitor, match its velocity, and study it up close. Imagine what we could learn from direct samples, from surface observations, from measurements impossible to make at millions of kilometers distance. Such missions require quick response capabilities we don't currently have. We'd need spacecraft on standby, ready to launch on short notice. We'd need international agreements about who controls such missions and how data gets shared. We'd need funding, political will, public support. But the payoff would be enormous. Direct study of material from another star system. Answers to questions we can currently only guess at. Atlas, whatever it turns out to be, is pushing these conversations forward. It's demonstrating why interstellar objects matter, why we should invest resources in detecting and studying them, why the public should care about visitors from beyond our solar neighborhood. Because each one is unique. Each one carries information available nowhere else. Each one is an opportunity we can't afford to miss. As December 19th approaches, as telescopes around the world prepare for their most detailed observations, we stand at a moment of potential revelation. Atlas will make its closest pass and then recede, growing dimmer, eventually vanishing into the cosmic background from which it emerged. We'll have a brief window to learn everything we can, and when it's gone, we'll be left with data, images, spectra, measurements, the raw material from which understanding is built. Maybe we'll conclude Atlas was an unusual but natural comet, a visitor from a stellar system with chemistry different from ours. That would be valuable. That would teach us about the diversity of planetary formation and the conditions under which comets can form. It would be good science. Or maybe we'll conclude we don't have enough data, that the anomalies resist explanation, that we need more observations, better instruments, new theoretical frameworks. That's okay too. Science advances through puzzles that persist, through mysteries that refuse easy solutions. Or maybe, in the data captured during those 72 hours, buried in spectral lines and jet structures and polarization measurements, we'll find something unexpected. Something that suggests the universe is stranger and more populated than we dared imagine. Something that changes everything. We won't know until we look. And we're looking right now. The telescopes are pointed skyward. The detectors are recording. The analysis is underway. Whatever truth Atlas carries, it's revealing itself in the darkness, one photon at a time. All we can do is watch, measure, and try to understand what the cosmos is showing us. The rest is up to the universe.